Welcome to The Explainer. So what happens when your two best theories for how the universe works completely contradict each other? Well, today we're diving straight into that puzzle. The epic search for a theory of quantum gravity. And yeah, that's not just some thought experiment. It's pretty much the biggest roadblock in modern physics, and it forces us to hunt for one single unified theory that can finally make sense of it all.
You see, for more than 100 years, our entire picture of reality has been built on these two pillars. On one side, you've got general relativity. It's beautiful. It describes the grand cosmic ballet of stars and galaxies on a smooth, curved stage called spacetime. Then on the other side, you've got quantum mechanics, which describes the absolutely bizarre, fuzzy, probability-driven world of atoms and particles. Here's the thing. They both work perfectly in their own realms. But the moment you try to use them together, say to describe a black hole, the math just falls apart. They are fundamentally incompatible.
To try and fix this, physicists figured maybe there's a missing piece. A particle that could bridge the gap and finally unite these two warring ideas. And they gave this hypothetical particle a name, the graviton.
The idea itself is actually pretty elegant, right? We know that light and electromagnetism are carried by particles called photons. So it makes a lot of sense that gravity should also have its own particle, the graviton, doing the heavy lifting.
And based on what we know from Einstein, we have a pretty clear most wanted profile for this particle. It should be massless, because gravity seems to reach across the entire universe, and it has to be what's called a spin 2 particle. Now, that's a super technical term, but you can think of it like this. A photon has spin 1, and it can push or pull, but a graviton needs spin 2 so that it's always attractive, always pulling matter together. Okay? But here's the huge catch, and our sources are really clear on this. Gravitons are expected to interact with matter so incredibly weakly that even if you built a detector the size of Jupiter and parked it next to a super dense neutron star, you might see one graviton every decade. It's basically like trying to catch a ghost with a butterfly net.
So, if we can't find the particle, maybe the problem isn't the particle. Maybe we need to completely rethink the fabric of reality it's supposed to exist in. And this has led to two giant, competing ideas about what the universe is really made of.
All right, so in one corner, you've got the famous string theory. It says that deep down, everything, every particle, every force is made of tiny, vibrating strings of energy. Different vibrations give you different particles. One vibration is an electron, another is a photon, and you guessed it, one is the graviton. But it needs extra hidden dimensions to work. In the other corner, we have loop quantum gravity. And it takes a totally different approach. It says, forget the strings, let's focus on quantizing space-time itself. Let's go down that second rabbit hole for a second. The absolute core idea of loop quantum gravity, or LQG, comes right from Einstein. And the idea is this: there is no background. So what on earth does that mean? Well, before Einstein, everyone pretty much thought of space as a fixed, unchanging grid, like a static stage where the play of the universe happens. LQG says that's totally, completely wrong. And that's a profound shift. It means space-time isn't just the container reality sits in, it's part of reality. It's a dynamic physical thing that bends, stretches, and evolves right along with everything else. It's an actor in the play, not the stage. This idea leads to a truly wild picture of the universe. LQG predicts that if you could zoom in to the smallest possible level, the Planck scale, you wouldn't see a smooth, continuous reality. You'd see that space itself is grainy. It's made of discrete pixels or atoms of space, connected in a network. Things like area and volume aren't continuous. They come in tiny, indivisible packets, described by these complex mathematical things called spin networks. Okay, so if space is pixelated, what does that quantum world actually look like? What's going on down there at the most fundamental level? The legendary physicist John Wheeler had this incredible vision of a reality that was anything but calm, and he gave it an amazing name: quantum foam.
The idea is that at the Planck scale, that's a length so small it makes a single atom look as big as a galaxy. The smooth geometry we know just dissolves. Spacetime itself becomes a chaotic, bubbling, frothing sea of pure potential.
And what's driving all this chaos? The famous Heisenberg uncertainty principle. When you apply it to space-time, it means that for incredibly tiny moments, huge amounts of energy can just spontaneously fluctuate into existence. This energy creates pairs of virtual particles and antiparticles which pop into being for a fraction of a second before destroying each other again, constantly churning the very fabric of reality. But what if we've been asking the wrong question this whole time? After all this talk about strings and quantum foam, some of our sources suggest that maybe the problem isn't quantizing gravity. Maybe the problem is that we don't really understand what gravity is to begin with.
There's this really fascinating alternative idea called inertial motion theory, and it proposes that we should just abandon the whole idea of gravity as a force, or even a curvature that pulls things.
Now, this is a huge shift in thinking. In the standard model, the sun is the active agent, right? It's pulling the planets. But this theory flips that on its head. It says all the objects in a system are active. They aren't being pulled. They're just following a shared built-in path, a tendency of motion that was set a long, long time ago. It's not an external force. It's more like an internal program.
So in this framework, the beautiful, predictable orbits of the planets aren't happening because the sun is constantly pulling on them. No, they're actually just the leftover momentum, the persistent echoes from the violent cosmic collision that formed our solar system billions of years ago.
So we have all these incredible, mind-bending theories. We've got vibrating strings, pixelated space, and cosmic echoes. But where does that leave us right now in our actual search for the truth? Well, here's the hard truth, and our sources are very blunt about it. We're flying blind. For all these beautiful, compelling ideas, we have not one single shred of experimental evidence to say which one is right. Their predictions either involve energies we can't possibly create in a lab, or in the cases where we could test them, like searching for new particles predicted by some of these theories, the experiments have all come up empty. And so, the great riddle of reality continues. Is space-time a smooth, continuous masterpiece like Einstein thought, or is it a shimmering digital illusion? Is gravity a fundamental force, or just the ghost of some ancient cosmic car crash? The quest for the answer is one of the greatest adventures in science, and honestly, we're all just waiting for that next crucial clue. The case is very much open.